if there are nice figures in my talk, they are made by Valentino, and the others are made by me. So what I'm going to tell you is a unified approach how we can describe the vertical kinetic energy spectra of both balanced and unbalanced motions in the hydrostatic atmosphere. But in the atmosphere, we are pretty happy with the hydrostatic assumption. Even in the leading operational numerical weather prediction model, one of the ECMWF, when they run model at around 2-kilometer resolution with hydrostatic and non-hydrostatic options, the results appear quite similar. This, of course, likely means that they have such a long successful development of the hydrostatic model that the model is so well tuned, but at least this justifies me not using Business approximation. And otherwise, the theory behind what I'm going to present is very similar to what Jeffrey presented today. And of course, it's also coupled to Manita's work. So in atmosphere, mostly, especially in climate sciences, we are describing vertical velocity in the pressure coordinate, and we call this quantity omega. And this is why I'm going to use a new Greek letter for the frequency. So in the models, in all major models, and here I will be mainly referring to ECMWF model, then what one does, one computes for the post-processing purposes, one computes omega, pressure vertical velocity on the model levels. And model vertical coordinate for the ECMWF is the hybrid eta coordinate, which is what is more precisely sigma pressure, because it's a terrain following. It is defined by two numbers and the surface pressure, and it becomes pure pressure coordinate higher up in the upper troposphere and above. So this is, for example, equation how one computes sigma pressure vertical velocity on a model level in the ECMWF system. So this is basically integral of the horizontal wind divergence from that model level to the top of the atmosphere plus the surface pressure term. And it is the same in the sigma system that we otherwise use in our modal representation of the world in the group. And this is the reason why I'm going to use pressure coordinate system in this talk. So to describe, so what I'm going to do, I'm going to answer this question. Can we decompose the vertical velocity into balanced or Rossby modes and non-Rossby modes? And the reason why I'm, instead of saying gravity or inertia gravity, saying non-Rossby modes is because my main motivation comes from the tropics. I'm interested in with my group to understand tropical dynamics. And in the tropics, we have these special waves, Yanai and Kelvin wave. And they feel the frequency gap between the two regimes, and they are really important for the tropical variability. And we cannot call them gravity. Even Kelvin wave is a gravity. So, but this is what I mean by non-Rossby. All inertia gravity plus Kelvin and Yanai wave. So the question is, when you look at this figure from a paper, can you tell me? This is some climatological average of the omega velocity of 600 hectopascal in reanalysis. The question is if you can tell me what yellowish regions in this figure are associated with the quasi-geostrophic dynamics, and what is due to some kind of, for different reasons, gravity waves, or what are signature of gravity waves? Anybody? There is at least one obviously gravity or orographic gravity wave related area, and that is in the south hemisphere over Andes. And this is the very famous so-called hotspot generation of the gravity waves. And those gravity waves then propagate up and towards the high southern hemisphere latitudes, and then can be long living there. So, so what we do in atmosphere, we in hydrostatic, so for the, of course, for the balance dynamics, we diagnose quasi-geostrophic omega. We diagnose omega from the quasi-geostrophic omega equation. This is the top equation, which is really complicated to solve, but yeah, this is what has been done by Hoskins et al. And then ever since 70s. And then for the internal gravity waves, we just use Taylor-Goldstein equation. And this W, this is just the amplitude of the vertical velocity times exponential term. And then there is the third equation, which one describes the vertical motions in the frontal regions, which is the semi-Sawyer-Eliason equation. And I'm going now to unify this. Okay, and I'm using modal decomposition for this. So the theory is in many textbooks. And actually in atmosphere, it goes back to early, it's a bit over 50 years old. It goes back to Richardson and Dickinson in the early 70s, who solved normal mode initialization problem for the two-level model, for primitive equation model. And then, of course, this was nonlinear normal mode initialization from late 70s throughout 80s in numerical weather prediction models, where lots of efforts was put into not killing diabatic circulation in the tropics. And the models improved, and once digital filter and 4D came, we just dropped it. But what we have been doing in the last decade was using this approach for diagnosing properties, especially in the tropics where it's most useful. So this can be useful to understand energy spectra, to understand equatorial waves, and to diagnose, for example, climate models in terms of those modes from the better-tuned NWP models. So we assume separability, and then we split our problem into two eigenvalues problem. One for the vertical structure equation that I don't really write here, and the other for the horizontal structure equations, which is this equation for the capital X variable. And these are basically linearized rotating shallow water equations on the sphere. And their eigensolutions are half harmonics. So half harmonics are made of half functions, which I denote by capital theta. And then there is an element of that half function for the zonal wind, meridional wind, and geopotential height. And that is for a single eigenvalue, for a single equivalent depth. So this is just similar to what Jeffrey was explaining yesterday. And then harmonic part is just, yeah, it is, I have frequency denoted by nu. And yeah, so then, because this is the complete decomposition, this can be used to decompose global 3D circulation. And what you see in the movie, you see some level up in the stratosphere around 30 or 35 kilometers. You see in colors, you see the gravity waves superimposed on these blue vectors. This is the balanced flow. And you can see it every day fresh, because now for 10 days, for 10 years, we have a web page, modes, that is decomposing ECMWF data and fresh forecasts into modes. And for example, this is for today, you are looking at the Yanai wave. This is the top horizontal plot, and below it is the Kelvin wave, according to ECMWF. And one purpose I used it for is to show that the global energy decomposed into the Rossby and non-Rossby modes is represented by these two spectra, red and blue spectra. And what you can see is not only that the divergent part, this part associated with minus pi third is maybe made of the Wheatley interacting gravity modes, but you can see progress in the atmospheric analysis from era interim, which is about 15-year-old model, to 10-year younger model, which is now 7-year-old. So you can see how the Rossby wave spectrum, which was not exactly -3, is now here almost exactly -3 to the lowest resolvable scale. And the inertial gravity or non-Rossby spectrum, which was -1.9 in this large metal scale, which is for us starting at wave number 15, which is around 1,000 kilometers, has evolved to become almost perfect -5/3 spectrum until about scale 500 kilometers, where there is still a gap between what is ideally expected and what the model is reproducing. So this is just to say that we have been using this linear decomposition, and to really, I'm sometimes just surprised how well it works, because, for example, for these gravity wave signatures, of course, there is no time component involved in the filtering. These are just independently projected data cut together. And then when one looks at ECMWF divergence fields, one can verify that the two fields match pretty well. So now the next step, how do we get vertical velocity? So we can represent for a single vertical mode, and that's why I dropped the M index here. We represent height field in terms of half harmonics. And this high coefficient, this is the half expansion coefficient. So K is the zonal wave number, N is the meridional mode. And then we have our linear continuity equation. And this tells us that this tilde means non-dimensional, that non-dimensional horizontal divergence is simply H field multiplied by imaginary unit and frequency. So this is equation 2. And then I can use from continuity equation in pressure system, I can express omega. So because these are two independent problems, I just now add the integration over vertical structure functions. So I have omega field expressed for any mode in terms of eigenfunctions. And this is verification that it works almost perfectly to the level we care about, given accuracy of all other components. So the top left panel is omega field taken directly from ECMWF archive. This is from reanalysis. So it's independent verification of the middle plot in the top row of omega retrieved using our modal decomposition. And then, of course, what is this B panel made of? It's made of all these components. So you see in panel C, it's a Rossby part of that. This is the level in the lower stratosphere. And then you see in bottom panel, IG part. And there you see, for example, gravity waves over Antarctic Peninsula. And you see that they are actually westward propagating gravity waves. So it works. And then, okay, so now actually there is a cross-section across Antarctic Peninsula. This is just another example. And these are, of course, plots by Valentino. So, and this one is simply, again, comparing independently retrieved omega data with what we recover from modes, and simply showing, again, this westward propagating gravity wave across Antarctic Peninsula. And why this is nice? This is nice because we can now quantify omega. We get now omega in terms of modes, which means we can do all computations in modal space, from the vertical kinetic energy to the fluxes, which is really motivation and the reason why we are doing this. So we want to compute vertical momentum fluxes, which are important problem we work on in TRR for the climate models. So how do we get spectra? So once again, I'm showing my omega equation. This is the top red frame. And then I expand omega along the latitude circle using a 1D Fourier expansion, which means that everything else in this top frame except exponential, except waves, simply represents my expansion coefficient. Okay, and then one can show things that Parseval theorem works and everything else. So, but what is the most interesting result? It is this slide. So, this is saying that the vertical kinetic energy, you can see from the bottom equation, where I have frequency and I have half expansion coefficient. And the square of absolute value of half expansion coefficient is the kinetic energy, not kinetic, total energy of the horizontal motions. So this tells me that the vertical kinetic energy is proportional to the square of the frequency of the mode and the total energy of the horizontal motions. And then if I involve dispersion relationships for the non-Rossby and Rossby modes, I get these two power laws. So I want to argue that the Rossby modes should follow -5 power law, and the inertia gravity modes should follow 1/3 power law. And let's see if data give any support to this. Okay, so this is the result. This is now my figure. So now. So it's application to ERA 5 reanalysis, and this is an average over 1 month of data. So what are the colors? We are starting from the lower troposphere. We are in the southern hemisphere mid latitudes. This is August, so this is winter. Lots of activity, lots of baroclinic Rossby waves, and lots of vertically propagating gravity waves and synoptic scales. So going from red to blue, we are moving upward. So the bottom curves belong to the stratosphere, and we are somewhere in the layer 30 to 50 hectopascals. And the most top curve, or the black curve, is the level 70 to 80 hectopascals. And I will be commenting only on the kinetic energy from about wave number 5 and greater wave numbers. So the first thing you see that the Rossby vertical kinetic energy spectra approximately follow -5. And for the non-Rossby, they don't. Actually, there is just one range in my figure which does follow +1/3, and that is this region of large synoptic scales. These are the gravity waves that came up into the lower stratosphere in southern hemisphere that do follow this, but all other areas. And then, yeah, I should say, of course, this bump. So all ageostrophic motions, everything projects, actually everything which is not geostrophic, which doesn't satisfy linear balance equation on the sphere, will project onto non-Rossby modes. So these are ageostrophic motions associated with baroclinic Rossby waves. And then you see, as we go higher up, it moves towards the zonal wave number 2, which dominates in the stratosphere. But we see a large, so of course this is 1/3, but how bad is this? We can't judge because we don't measure vertical velocity. But and it may be right because the forecasts are good, but then we go to tropics and we get very largely different spectra in the tropics where convection is driving vertical motions. So we still have approximately -5 and even steeper at smaller mesoscale. But if we look at the non-Rossby modes, we see, first of all, we see a sharp cut going higher in the stratosphere, which may be signature of missing vertically propagating waves, but lower in the troposphere, we see that we are close to +1/3, not -1/3. And this brings me to my summary. So I have shown you a unified framework to compute vertical velocity in the hydrostatic atmosphere, and I argued that based on -3 and -5 third power laws of the horizontal motion kinetic energy, The vertical power spectra follow -5 and +1/3. And then I show, at least in the reanalysis, that the spectra of the non-Rossby motions are pretty far from what one would expect theoretically. And we will report more, or Valentino will report how this provides him a tool to compute vertical momentum fluxes on some of the next meetings. May Manita may organize another one. Thank you very much.